So let's apply the law of gravity and let's tease out a puzzler. It's one of my favorite types of questions to ask. So here's the setup, right? If I take a 10 kilogram bowling ball and I drop it, right? That 10 kilogram bowling ball is going to accelerate towards the Earth at g, little g, 9.8 meters per second squared. So now my question to you is, what's Earth's acceleration? I'm going to call it A subscript e, right? What's the Earth's acceleration towards the bowling ball? All right. So pause the video, give yourself a second, try and figure out, is the Earth's acceleration going to be smaller than g? Is it going to be exactly g? Or is it going to have to be greater than g? Think about why. All right, I will tell you right now that you can logic the answer out without doing any math. We're going to do the math in detail to fully convince you and for some good practice. All right. So with that out of the way, let's dive in. Let's work this out. I'm going to do this the long way first. I'm going to say, how can I get to that answer? And I would say, look, let's just calculate what Earth's acceleration is. Well, I'll take the second law, F equals ma. What's the force on Earth? We're going to try and calculate the Earth's acceleration. So we're going to say Earth has a gravitational force between the bowling ball and all the mass of Earth. So that force is going to be acting on the mass of the Earth multiplying by whatever this Earth's acceleration is. Now, I didn't give you what the Earth's mass is because it's not going to matter. Here's Newton's law of gravity. Big G, Earth mass, bowling ball mass, raised to the Earth squared. We're not far enough away. Right? Well, take this Earth mass. It's going to cancel out on both sides of the equation. And I'm going to be left with this result, right? The Earth's acceleration is equal to gravitational constant, the mass of the bowling ball, divided by the radius of Earth squared. All right, so I'm going to erase all this up here and just slide this equation up top. So this is, the problem is done. You can look at the values, plug things in, you're good to go. I'll argue once again that you don't need the calculator. We can pull out the information without it. So we're going to use our powers of tens to simplify our calculation. Gravitational constant. Do you remember what that value was? It was 10 to the minus 11th. So our gravitational constant has a 10 to the minus 11. The mass of the bowling ball, yeah, I picked a really easy one. I made it just 10 kilograms, so that's 10 to the first. And Earth's radius, ignoring the 6.67 up front, it's just 10 to the 6, right? So we're going to have a 10 to the 6 squared up here. And now just add up, get all those powers of 10s together. Right. So we'll have minus 11, we'll get a plus 1 from the bowling ball, and then 6 times 2, because it's a 10 to the 6 being squared. Minus comes from the fact that this thing's in the denominator. So we'll have minus 11 plus 1 gets us to minus 10. Minus 12, I will say that the Earth's acceleration towards the bowling ball is on the order of 10 to the minus 22 meters per second squared. Now, g, the bowling ball's acceleration, is about 10 to the 1 power. So, yes, Earth's acceleration towards the bowling ball is significantly smaller. Way smaller. If Earth accelerated at this rate for 1 second, the distance it moved would be smaller than 12 orders of magnitude than an atom. This is way smaller than we can measure. So, if you didn't do the powers of 10 calculation and you just plug the values into your calculator, you would find that the explicit value is 1.6 10 to the minus 23rd. We lost a factor of, we lost one order of 10 because we ignored things like 6.67 being squared as well. So, that's the long way. How could you get there quickly? Remember your third law. Newton's third law says that there will always be equal and opposite forces. The bowling ball has this F gravitational pulling the bowling ball down towards Earth. Earth will have the same force pulling Earth towards the bowling ball. But just because the forces are the same, the accelerations have to be different. That's the second law. The forces are the same, but second law says the force is equal to a mass times the acceleration. Well, since this one is significantly more massive, the more massive object, to keep the forces the same, will have a smaller acceleration. Whereas the less massive object will have the much larger acceleration. So that's a way to get there without doing any of the math. We're just going to straight apply Newton's 3 laws. Same forces, different accelerations.